So this is the elliptical lift distribution. So we know in the y-axis we are taking the span. Okay, for example, if this is the wing, so this will be the y-axis, this will be the z-axis, this will be the x-axis. Okay, in the thin airfoil theory and all, you have seen we have taken the airfoil and the x-set. Okay, so chord will be aligned to the x direction, span will be aligned to the y direction, then lift will be aligned to the lift or circulation will be aligned to the z direction, vertical direction. So here we are taking y and vertical direction axis. Okay, y and vertical axis. Is that clear? This axis system. Okay, span at the y direction, chord at the x direction, lift or circulation is in the z direction. Okay, so we know the total span is b, and always we are taking reference and the center in the wing. So this is positive b by 2, this is negative b by 2. Then in the vertical direction I am taking circulation. Okay, and circulation is equal to 0 at the tip, and it keep on increasing and reaches its maximum value. So circulation is maximum in the center, that I am denoting as gamma naught. Okay, so circulation is 0 in the tip, maximum in the midpoint. So midpoint, the maximum circulation I am taking as gamma naught. Okay, in the remaining point we will get different circulation value. So now this is the circulation distribution for the elliptical profile. Sorry. Okay, now we know the ellipse equation. So x-axis maximum a, y-axis maximum b. It will be x squared by a square plus y squared by b square is equal to 1. Now we will apply this same condition to this elliptical lift distribution or circulation distribution. You can see. So here we have y, here we have gamma, here we have b by 2. Instead of b we have gamma naught. So it will be like gamma divided by gamma naught square. Okay, gamma divided by gamma naught square and y square divided by b by 2 whole square. Is that clear? See, instead of x, there we have y. Okay, instead of a, there we have b by 2, and instead of this y we have capital gamma, and instead of this b we have gamma naught. So substitute this thing here, you will get gamma divided by gamma naught square plus y square divided by b by 2 whole square. This equation you will get it. Is that clear? Hello? Yes, someone can reply, right? What are you doing, all of us?
Yes, sir, understood.
Okay. So this is alone important. If you can, through this you can find it, or you have to memorize. Okay, because once you know this, the remaining procedure and all simply the substitution. Okay, then I'm rearranging this for the gamma. So rearrange gamma square is equal to gamma naught square, this term, but I need the only circulation gamma. So take the square root on both sides. You will get gamma is equal to gamma naught 1 minus y square by b by 2 whole square, that is they have written as 4 y square by b square or 1 by 2. Now this is our final circulation equation for the elliptical lift distribution. So we found the elliptical lift distribution. From this I can find W, alpha, CL, CDI, etc. and all. Okay, so this also already we derived in the Prandtl lifting line theory, WI equation. So I know the circulation equation for elliptical distribution. Just now we found it. So if you want to find this WI, then I need the d gamma by dy. So what we have is the gamma. So we have to differentiate that with respect to y. Then only we can substitute here. Okay, so first step is finding the WI using this circulation. So I'm finding d gamma by dy. So this is like x power n. So if you differentiate, you will get n into x power n minus 1. Okay, from this. So we are getting 1 by 2 whole power n minus 1. It will be minus 1 by 2. Then this term alone, it will be like 8y divided by b square. Okay, so if you differentiate, you will get this term. Then rearrange, you will get this term. Okay, normal rearrangement only. Now this d gamma by dy we can substitute here. Then you will get this equation. Okay, so d gamma by dy, this one, substitute, you will get this final equation. Here also they just rearranged. So this is the final. Is that clear? So we started from here. From circulation, we found d gamma by dy. Simplify, substitute here. Then this is our final equation. Is it clear?
Yes, sir.
Okay. And as usual in the potential flow theory, so we are doing the coordinate transformation. So coordinate transformation means x, y to theta we have to convert. For that I am using these terms. Y is equal to minus b by 2 cos theta. Previously in the thin airfoil theory we used, I think, x is equal to c by 2 1 minus cos theta. Here it is minus b by 2 cos theta. I'll explain how we are getting this. Okay, so assume this is the wingspan. Okay, center point is 0, both sides v by 2 minus v by 2. And you know the distance we are measuring from the center only, y distance. You can see here. You can see center point is the reference point. From there only we are measuring y, y1, etc. and all. Okay, so from center point we are measuring on both sides. So from the center point I am taking some particular distance y. Now I have to convert this y into theta. So the first step is we have to draw the semicircle. Then you have to extend this point so that you will get an intersection point. You know the radius is minus b by 2. Okay, then I can find this y. It is simply minus b by 2 cos theta. Is that clear? So procedure is, first you have to take the span. Okay, then one arbitrary distance y. Then to convert this y into theta, you have to draw one semicircle. You know the semicircle radius is, this side we can take minus v by 2. So then from this length to one intersection point we will get it if you extend. That you join, it will be minus b by 2. Okay, radius. I am taking theta in the clockwise direction. So it is y is equal to minus v by 2 cos theta. The same procedure we used in the thin airfoil theory, but reference length is from this center. That's the only difference. So most of the books they are taking y is equal to minus v by 2 cos theta only. Okay, this side if you take, what will happen? This will be your theta. Okay, then this side will be 180 minus theta. You will get the same thing, minus v by 2 cos theta only. So any side if you take, the theta what we are taking is from the clockwise direction, so you will get the same equation. But some book they are taking the theta in the other direction, so they are getting positive v by 2. So some book they are using minus v by 2 cos theta. Some book they are taking theta from the anti-clockwise direction, so they are getting positive. Okay, so don't get confused. So books may be using different notation, plus v by 2 or minus v by 2. But from the thin airfoil theory itself, we used to take theta only from the clockwise direction. So here also I am using the same method. Okay, so I am taking the only clockwise. So I am taking y is equal to minus v by 2 cos theta. I am not taking this method, this additional. Is it clear? Simply based on the theta, it is changing, the sign is changing. Always we are taking theta in the clockwise direction, so we are getting minus v by 2 cos theta. So that's why I have taken y is minus v by 2 cos theta, y1 is minus v by 2 cos theta 1, Then for dy, simply you have to differentiate v by 2 sin theta d theta. So these term we have to substitute here instead of this y dy. Every year you have to substitute so that we can get this w in terms of theta. So if you substitute, you will get this y into dy and y1 minus y minus y1 everywhere. If you substitute, then simplify, b by 2 get cancelled like that. Finally we are getting this equation wi. Okay, after simplification, and this is the standard result. So integral cos n theta t theta divided by cos theta minus cos theta 1 is the standard result. Again, in the appendix you can find the solution is sin n theta by sin theta into pi. But here n is equal to 1 in this above equation. So if you substitute 1 everywhere, this term get cancelled, you will get only pi. Okay, so the solution is pi. Okay, so this is the standard solution. Cos n theta divided by cos theta minus cos theta 1. So apply here, you are getting only pi. Pi get cancelled. Then it is minus gamma naught divided by 2v. We know this induced velocity derived from the Beer-Savart law. It's simply the magnitude. Okay, so we don't take the sign, we take only the magnitude. Gamma naught divided by 2v, which is acting downwards. Once we know wi, we can find alpha I, wi by v infinity. Okay, so we found first two terms. Is that clear? Hello? So full of mathematical simplification only, simply integration, differentiation using the formulas. Then we are finding the lift. This equation again the Prandtl elliptical line theory we derived. Lift is equal to so rho v gamma dy or CL is 2 divided by Vs integral gamma dy. Okay, better first we will find lift, then we can go for the CL. So this formula I am taking here, rho v gamma dy. Rho v gamma dy. So we know the gamma naught into 1 minus 4 square by b square. Substitute, then we have to do the coordinate transformation from y to theta. Okay, substitute, then simplify, we are getting this term rho v gamma naught v by 2 integral sine square. So integral sine square is pi by 2, then cancel, that is simplify, we are getting this lift equation. Okay, so everything is simply substitution and simplification. So gamma equation, then y to theta, then simplify. That's it. So once you know the lift, we can find the CL. Okay, once you know the lift, we can find the CL, simply divided by half rho v square s. We are getting this term. So CL also we found it. Then these steps, simply they are rewriting all W, alpha, everything in terms of CL. Because from the experiment, mostly you'll get only CL/CD. So they are rewriting this alpha and W in terms of CL. So if you rearrange this equation for gamma naught, okay, you will get 2Vs CL divided by B pi. Okay, and Wi already we found it, gamma naught divided by 2B. So instead of gamma naught, substitute this in terms of CL, simplify, you will get CLV divided by pi AR. Simply alpha I, we have two equations. You can substitute gamma naught here, okay, or you can substitute this Wi here, anything is okay. If you simplify, you will get this equation. Okay, so they are written alpha I and Wi in terms of CL, these additional steps. Okay, so we found CL, then we have to go for the induced drag and coefficient of induced drag dI. So dI, again two formulas are there. So rho Wi gamma, or it is simply L alpha I. I think compared to that, this is easy because here I have to substitute alpha and gamma. Already I found the lift and alpha. So this method is easy, L and alpha I. So that method I am taking. So dI is equal to L into alpha I. So what I need is the finally CDI. So divided by Q infinity S on both sides. So I am getting CDI is equal to CL alpha I. So CL is okay because finally CDI in terms of CL only I need it. So this term straightly I am keeping it, and instead of this alpha I am substituting this term whatever we found here, CL divided by pi AR. Substitute, we will get CL square divided by pi AR. This is the final term. Okay. So from drag I am finding CDI. Okay, final term CDI I need in terms of CL only. So this time I'm just keeping this alpha A alone. I'm substituting in terms of CL. Then I'm getting CL square divided by pi AR. That's it. This 12 more derivation is over. But now as it is the online exam, we cannot ask 12 marks and all. We may ask few problems based on these formulas. So what you have to do is we have to memorize, we have to remember these formulas and all. What is the lift equation, CL equation in terms of gamma naught, or alpha WA in terms of CL. So these formulas and all you have to memorize. Then only you can attend the 2 marks, 3 marks problems. Okay. That's it. This is on 12 marks. This step is additional step. There's you just remove it. In some book, so first they derived DI, then CDI. Okay. This is one procedure, finding the CDI. But this is very simple method. So I am taking this method. Okay, straight away from the CL you can find these steps, then you can go for these color methods steps. So you can, so you know to consider these steps. Some books but they follow these methods, so I just mentioned here. From these 2 steps straight away you can go for this step. So one derivation is over. So mostly you'll get lot of problem from this. So lift distribution thing. What happened? You have to time, right? Okay, 143. So first step we are finding gamma. So in the, okay, for you online only. So you should remember this equation. Okay, circulation equation for elliptical. Then these equations also you have to memorize. That is whatever the basic equations of Prandtl lifting line theory. Better you memorize these things also. It will be useful. So from this we are getting this term after substituting gamma, then coordinate transformation, and simplifying. We are getting alpha and W, then lift rho v gamma dy. We are getting lift, then finally CL, then alpha W in terms of CL, then finally drag and CDI. So okay, this is on derivation. Any doubt? Any doubt in this derivation? Hello?
No, sir.
Okay. Next, another on derivation. But before going to the derivation, better I'll explain the problem, because continuously if we take, no one will listen. So next class I will complete the remaining derivation. So now we will solve few problems based on that elliptical lift distribution. So this is the first problem. So here they were given aircraft weight 14,700 Newton and it flies with a velocity 30 km per hour at the altitude of 3000 meter. So at that altitude, we know density will vary if you change the altitude. So at sea level it is 1.225. So at 3000 meter it is 0.9092 kilogram per meter cube. And they have mentioned wing area, aspect ratio, alpha L is equal to 0, 0 lift angle of attack minus 1.2 degree. And they have mentioned the wing produces the elliptical lift distribution, and the aircraft is in the steady level condition. You know the meaning of steady level condition, right? So lift is equal to weight, thrust is equal to drag. This is the steady level equation. So lift is equal to weight, and the CL is the linear function of alpha. Okay. So CL varies linearly with alpha. So using this information, we have to find so gamma naught, WA, alpha A, alpha effective, alpha CDA, etc. and all. Is that clear, this problem? So these are all the given value. Using that, we have to find these parameters. Is that clear? See, first term is gamma naught. As I mentioned, you should know what is the gamma naught equation. Okay, so it is 2Vs CL divided by pi b. Just now we derived. See, gamma naught is equal to 2Vs CL divided by b pi. Okay, that's why these terms we have to memorize. Then only you can solve the problem. So no other way. So gamma naught equation we have. In that, what we need is the velocity. It is given kilometer per hour, but we have to convert that into the meter per second. Area is given 17 meter square. Then CL is not known. We have to find it. Span we need, but they are given aspect ratio, and we know aspect ratio is equal to b square by s. S is known 17. So from that we can find the b. Okay, so from the aspect ratio and the area, we are finding the b, 10.226 meter. So finally, what we have to find is the CL. All other things are known: velocity, area, span, everything we found it. So to find the CL, I'm writing the general equation: lift divided by half rho v square s. We don't know the lift, but they are given the weight. They mentioned the aircraft is in the steady level condition where lift is equal to weight. So instead of weight, I can take that as a lift. Okay. So weight is equal to lift. Substitute here. We know density at that particular altitude. Velocity in terms of meter per second. Area 17. Substitute, you will get the CL. Okay. Once you know the CL, substitute here. So velocity, area, CL, span, everything you substitute. Finally, we will get gamma naught is equal to 24.06 meter square per second. Is that clear? So this problem is, tell me. Hello? So this problem is simple only. The only thing is you should know this formula. You have to remember this. Okay, that is the only thing. Once you know that, you know aspect ratio formula, CL formula, L is equal to W, etc. Simply substitution. But this you should remember. That is the only thing. Then we can go for the alpha I. Okay. So for elliptical wing, we found WI. WI is equal to gamma naught divided by 2b. This also we derived just now. So gamma naught we found it. Span also we found it 10.225, 226. Substitute. You will get the induced velocity. Okay. Then once you know the induced velocity, we can find the alpha I. I think alpha I is Wi by V infinity. This formula also you can use. Otherwise, we know alpha in terms of CL. CL should be pi AR. This also you can use. It's up to you. Okay, any formula you can use. Then CDI. This is CL square divided by pi AR. CL we know that. Aspect ratio is given. Pi also we know that. So substitute, you can get the CDI. This also we found it. And what they have asked, WA, alpha I, gamma naught we found it, CDI we found it. Okay, these two terms they are asking alpha effective and alpha. We know the equation which relates alpha effective alpha. That is the CL equation for the wing. 2 pi alpha effective minus alpha L is equal to 0. So alpha L is equal to 0 is given. I think it is minus 1.2 degree. Substitute 2 pi CL value, everything is known. From this you can find the alpha effective. Okay. Once you know the alpha effective, we can find the total alpha, which is alpha effective plus alpha I. This is a 12 mark problem. So in the 2 mark, they may break this. Okay, they may ask only what is a CL or CDI or alpha, something like that they will ask. Okay, they will break up this problem. Is it clear? This problem?
Yes, sir.
Okay. So only thing is memorizing these formulas, that's it. These formulas, if you know, straight away you can substitute and find it. Okay, this is one problem. Then second problem, so find the lift of the wing. They are given density, chord length, span, velocity, and average gamma value. Okay, so not the distribution, they are giving average value. What is the average value they have given? Okay, so from this so using this we have to find the lift of the wing. So Kutaskowski theorem is applicable to the aerofoil. Okay, so this is for aerofoil. So lift is equal to rho v gamma. We know the density, velocity, gamma value, so that I can find the lift at a particular distance, at a particular location. Then for the wing, simply I have to multiply with the span. Okay, if they have given circulation like this distribution, then I have to go for the integration. Okay, because circulation is different everywhere, so I have to go for the integration. But here they mention the average value. So what is the average value they have mentioned? So then average value will be constant everywhere. Okay, it is not distribution, it is constant. So once I know the lift is lift at one point, then simply I can multiply with the span so that I can get it for the complete wing. So simply lift of an aerofoil into span gives the overall wing lift. Is it clear? So they mention circulation is constant. Normally, you know, circulation means it will have some y term. Okay, similarly for the ellipse, if you take, what you have found is gamma naught into 1 minus 4 y squared by b squared, like that we have got it right. So here and all it is gradient. Circulation is in terms of y, it will vary, but here they have given the constant value, which is average. So once we find the lift at one particular point, then simply we can multiply with the span, we can get the overall lift. Okay, this is very simple question, but you have to visualize this. The circulation is constant, the lift also constant everywhere, so simply you have to multiply with a b, that you have to think. Is it clear? So this is for airfoil, this is for wing. So it is constant, lift also constant, so simply multiply with the b will give you the complete wing lift. Is it clear? Or should I repeat? Hello? Anybody?
Clear, sir.
Okay. See, whatever the alpha value you are getting this equation, it will be in radian. Okay, don't put degree. You know, everything is dimensionless number. CL is dimensionless, aspect ratio also b squared by s. It doesn't have dimension. So what you are getting is a radian. You should not put this value as a degree. Okay, don't forget. Alpha I, whatever you are getting, it is always radian, but you have to convert it into degree if you want, or otherwise in the radian itself you can leave it. But don't put degree for this value. It is radian. That's it. Okay, and this is the third problem. So here also they mention The wing produces the elliptical lift distribution. Wingspan is 15 meter, lift is 80 kilonewton, free stream velocity is 90 meter per second, density is 1.2 kilogram per meter cube. So we have to find induced angle of attack, alpha I. So they are given both formulas, Wi by V infinity or CL divided by pi AR. You can use any formula which is applicable based on these inputs. I think lift is given, so we can take this CL equation. So first I can find the CL, lift divided by half rho V square S. Okay. So lift is known, density is known, velocity is known. Okay. So area is not known. So what they are doing now, simply they are substituting this here. Now itself here you can substitute the values, lift value, density, everything you can find it. Finally you may get some numerical value divided by S. Okay, if you want you can substitute here itself, but here what they are doing is CL they are substituting here, so we are getting this equation. Okay, 2L, that is half. If we take to the numerator, it will be 2L divided by rho V square S into pi AR. So finally we got this alpha I. Now we can simplify this equation because S is unknown, right? So instead of this aspect ratio, they are writing B square by S. Okay, so instead of this, they are writing B square by S. Now S's get cancelled. Okay, remaining is 2L rho V square B. Now everything is known. Lift we know, velocity we know, span we know, density we know. Substitute, you will get the value in terms of radian. That's it. Is that clear?
Yes, sir.
Okay. Last problem. So here they have mentioned for elliptical lift distribution, velocity is 100 meter per second, span is 2 meter. We have to find induced angle of attack, and they have given circulation equation also. Okay, so for elliptical lift distribution, they have mentioned the velocity, semi-span. Span means B, semi-span means B by 2. So B by 2 is 2 meter, velocity is 100 meter per second. Circulation equation they are given. What we have to find is the alpha I. Okay, Wi by V infinity or CL divided by pi AR, or in terms of gamma naught means it is gamma naught by 2BV. So any formula we can use it. So there is no lift etc and all, so we cannot use this. And Wi also it is difficult. So we are taking the basic equation, gamma naught divided by 2BV. So span is given. Span is given. Okay, that is B by 2 is 2, then B is 4. Okay, span is 4 and velocity is 100 meter per second. This gamma naught alone we have to find it. So this is the equation they are given. You can compare this with the elliptical lift distribution general form. Okay, so instead of gamma naught they are given 100, remaining everything is same. So bracket 1 minus y by 2 whole square power 1 by 2, everything is same. Instead of gamma naught they are given 100. That means this is gamma naught value. So you should not think that the data is missing. There is no gamma naught value. Sorry. Okay. So this is the alpha I. This we have to memorize no other way. Span is given, velocity is given. You should not think gamma naught is not there. So the data is missing. So if you compare this with the general elliptical equation, gamma naught is equal to 100. Substitute. Okay, normal substitution, you will get the value in terms of radians. That's it. Is that clear?
Yes, sir.
Okay, that's it. This is about elliptical lift distribution and its problem. Next class we can see this general lift distribution. Okay, this is the circular indication for general lift distribution. So why we are taking this, how it satisfies the conditions. Then same procedure. From the gamma we are finding Wi, then Cl, then CDI, same procedure. That's it. This unit is over then. And at last we have just one theory, delta wing. Delta wing you have seen, right? Delta wing. There mostly we are using the delta wing. Sorry? Hello? Mostly you could see this in the fighter diagraph. Good. So here I want to explain how the flow property streamlines. So moving along that delta wing. So this is the streamline pattern. Okay, you can observe one. Sorry. You can observe one vortex on the wing. Okay, so this is the special characteristics of the delta wing. Okay, so there will be a vortices on the wing because of this shape. Here also you can see. This is the simulation. The same concept. The normal wing we studied, right? So due to the pressure difference, there will be a side leakage flow. It will be pushed rearward, so it will be formed as a wing tip vortices. But the difference is, if we take rectangular wing, on that wing there will be only the side leakage flow, and the vortices are formed only behind the wing. Okay, this is for rectangular wing. Okay, vortices are formed only behind the wing. But if you take this delta shape, okay, here also side leakage flow, but due to that there is a vortex formation. So side leakage flow is everywhere, but here whatever form that produces the vortices on the wing itself, that is the only difference. Okay, on the delta wing, the side leakage flow becomes a vortex and that is visible on the wing itself, but in the rectangular wing, the vortices are formed only behind the wing. Is that clear difference, rectangular and delta wing? So we don't have the vortices on the wing.
Sir.
Only for the delta wing we have the vortices. You can see the vortex structure. How to pass this? It did not pass. So okay. So like that on both sides there is a vortices. Okay, and you know the property of vortex, right? So vortex means velocity, that is free vortices. Velocity will be maximum in the center and decreasing towards the edges. So velocity is very high in the center. That means low pressure region. So these vortices has the low pressure region in the center. Okay, you know the normal wing means, for example, this may be the lift distribution. But instead of the normal wing, if you take this rectangular delta wing, so there are vortices. Because of these vortices, there is an additional low pressure region. So instead of this, we are getting this type of pressure distribution because this produces some low pressure that increases the pressure difference. So we are getting this type of pressure distribution. Is that clear? So for the normal wing, there is no this vortices on the wing. What will happen? It will be like this for the normal wing. But here, due to the vortices, there is some low pressure on both vortices that increases the pressure difference. So instead of like this, we are getting a peak in the vortex regions. This additional pressure difference we are getting. Is that clear?
Yes, sir.
Yes, sir.
Okay. And this, due to this additional pressure difference, we are getting additional lift. That lift is called vortex lift. Okay. So due to the vortex, there is additional pressure difference. Due to that, we are getting the additional lift. So that is called vortex lift. This is one important thing. And in the vortex itself, if you see in the closer view, there are multiple vortices. This is the major vortex. Okay, and you can see another one small vortices inside also. Okay, like that, the vortex is also separately they are studying this additional information. So another important thing, you can see normally if you take the, I will write here. Normally if you take the rectangular wing or something, maybe at 14 degree, 16 degree, what will happen? It will separate. Okay, but if you take this delta wing, you know there is a strong vortices on it. Okay, some low pressure region. So this low pressure region sucks the separated flow. Okay, this is the axial vortices on the delta wing. That is very low pressure. This low pressure sucks the separated flow. So instead of separating, these flows are attached to the surface. So if you use delta wing instead of rectangular, it won't stall at 14. The stall may happen at 30 degree to 60 degree. In between that, the stall will happen. Because of these strong vortices, there is a low pressure region that sucks the separated flow. So the stall angle is increased from 14 to minimum 30. Is it clear? Is it clear? So compared
Yes,
to
sir.
compared to the conventional rectangular wing, this delta wing have more stall angle. But you know, because of this difference in aspect ratio and area, definitely this will produce a low lift. Okay, that's why we are not using this for the normal low speed commercial aircraft, because it won't produce the enough lift. The lift will be less because the velocity also lift for the low speed commercial aircraft, and we are using this only for the high speed aircraft, because the normal formula is of v squared s cl. So if the velocity is less, lift also will decrease. Okay, so low speed we cannot use this because addition to the decrease in velocity, area also decreasing. But in the high speed aircraft, velocity is high, so this loss in lift can be matched. So only for the high speed we are using this. We explained, you can see this is for the high aspect ratio wing, some rectangular or some tapered wing. You can see where is the lift value. This may be 14 degree, this may be 30 degree. Okay, this is for the rectangular wing. Assume rectangular wing. This is the CL curve. Assume these values are 0.5, 0.8, 1, 1.2 something. Okay, so 0.5, 0.8, 1.2. This is for normal wing. And if you use the delta wing, what will happen? This is the lift. It may be only 0.1, 0.2, 0.3. Only this much lift we are getting within the trend line. Okay, because the area is reduced, so there is a loss in lift. But after stalling, that is after 14 degree also, this can generate the lift, but this will stall. Then it is keep on increasing. The stalling happen at 30 degree or beyond this. Is that clear?
Yes, sir.
Okay. So because of this low lift only, we are not using this in the commercial aircraft, because lift also very important. We should not see only the stalling angle. Lift also we have to see. So we are going for high aspect ratio for the low speed, and this delta wing only for the high speed aircraft, mainly the jet aircraft, where we need the maneuvers. Even if you keep your jet aircraft at 45, 30 degree, 40 degree, there will not be a stall. If there is a stall, then we cannot control that jet aircraft, it will fall. So in that maneuvering point, we need the stalling at very high angle. So we are going for the delta wing. And here you see it varies from 25, 35, 40. So depends upon the angle. So 45 degree. 65 degree like that, depends upon the angle. This varies. Stalling angle range varies, but you see it is very high. Normal aerofoil will stall from here itself, but this goes minimum 20, 25, 30, 45, 50 like that, it will increase. So here they explained, if there is no vortices, then if you find the lift, it will be like this CL distribution, and because of this vortices on the wing, the CL goes here. Okay, then this region is the vortex lift. Okay, this is the normal lift produced by this wing shape. Okay, this additional lift is produced by the vortices. So this is the vortex lift. Is that clear? So for the same wing, they explain without vortices, with vortices. This is with vortex. This is without vortex. So without vortices, it may be like this only. Because of the vortex only, it is going like this. But again, before 14, it is very less. Okay. If you draw the normal aerofoil, it may be like this. I couldn't draw properly. It is a rectangular wing. If you draw, it will be like this. This is for delta wing. Okay, here they explain the leading edge portion. It varied how for supersonic aircraft and all, we will go for the sharp leading edge. But for the subsonic aircraft, we will go for the round leading edge. So here they explain how it varies. So this is for sharp. This is for semicircular. Okay, sharp means easily it will stall, you know, right? So if it is round, then the flow may be attached. If it is sharp, the flow will easily separate. That's why at high angle, the lift is decreasing for the sharp, but for the circular, it is little bit attached. So we are getting a little bit higher CL for the circular leading edge.